so here we go. So this is just the rest of 16.6. So the part we talked about in class today was basically how to do a typical calculation where you use your simplifying assumption and all that stuff. There's a couple other types of problems they might give you here. One type is asking you about percent ionization, okay, and that's basically just asking for how much of this is going to break apart when you put it in the water. So how much of it becomes H plus and F minus. Now, if I'm asking about percent ionization of something like HCl, what are you going to tell me? 100%. It's a strong acid, right? So it's going to, all of it's going to ionize. So there's, for a weak acid or a weak base, I guess more for a weak acid, there's going to be a specific amount of ionization that takes place, a specific percentage, and we can figure that out based on the Ka, which I'm just realizing I did not give to you in this problem. You would need the Ka to solve this. It's because they didn't give it to you in the book because they're assuming that you can just look it up if you're doing it out of the book. So the Ka for this one is 6.8 times 10 to the negative fourth, I think. Fourth. All right. So as far as weak acids go, that's a relatively high Ka, which means that it does dissociate quite a bit. I say that relatively because 6.8 times 10 to the negative fourth is not a very big number. But so what we're trying to figure out here is how much of it does actually ionize. Okay. This is kind of a roundabout way of asking what's the concentration of the ions at equilibrium. So guess what we get to do on this one? Ice table. Yep. So now again, these are going to all start to look very much the same to you after a while, which is, I guess, kind of nice. It becomes just a process. You just need to make sure you understand the process. So HF, because it's a weak acid, is going to, and I'm going to take the shortcut here and write my equilibrium like this. Okay? It's probably more accurate to write H plus, or HF plus H2O yields H3O plus F minus. Okay? But this way works. And it's just a little bit faster. So then we're going to make our ice table here. The HF starts out as a 0.10 molar solution initially, right when we put the HF into the solution, and we can assume that we don't have any of the H plus or F minus right at the beginning. Okay. This is all one-to-one stoichiometry, so again we're going to do a minus x plus x plus x, 0.10 minus x, x, and then plug that into your K expression, which is going to be the H plus times the F minus over the HF. All right, so we've got 6.8 times 10 to the negative fourth is equal to x squared over, x squared over what? 0.10 minus x, or can we just do 0.10? I mean, this Ka is not incredibly small, right? But compared to 0.1, it seems fairly small. We'll check it at the end just to make sure, okay? But I'm just going to do 0.1 here. I'm going to assume that Ka is small enough that this probably not very much of this actually
David
dissociates.
Novak, could you please meet your mom at the front door? David Novak, please meet your mom at the front door.
So it's a fun thing to have announced. All right, so then you solve for this. 6.8 times 10 to the negative fifth is equal to x squared. You just multiply both sides by 0.1. Take the square root of both sides. It's going to give you, for all you really math-intense people out there, yes, that is going to give you a positive and a negative number. But the negative number doesn't make any sense in our context, so let's not worry about that. We'll just worry about the positive. So x equals 0.0082. That's what they're getting. Oh, I'm looking at the wrong one. panicked for a second. Yeah, 8.2 times 10 to the negative third would probably be the more professional way to write that. Well, here's the problem. When you look at this one, and you know, it's okay that we're talking about an example of this. Well, does it work for the first one or not? No, it doesn't even work for the first one. All right, so once you get this value, 0.0082, you can check to see if your simplifying assumption was okay or not. And what you basically have to do is take the amount that ionized, this 0.0082 value, divide it by the initial, which is 0.1, and then times it by 100. And when you do that, you actually get 8%. 8.2%, which is unfortunate because that means we actually can't use the simplifying assumption on this one, okay? But I'm not going to make you go through the whole process of, you know, using the quadratic formula and everything. They're just showing you one in the book where you really can't. So we were right to kind of question whether that's a small enough Ka to be able to make your simplifying assumption. It's not a bad idea just to check that Ka when you're looking at a problem and just say, that's not really that small. Can we really make that assumption here? All right. And like I said, on the AP exam, they'll always give you a workaround. So most likely they're going to deal with Kas that are times 10 to the negative 8th or 10th or something like that, so that you can easily make that simplifying assumption and have no problem whatsoever. So on this one, you would go ahead and solve a quadratic formula, right? That's what they do in the book. But again, we're not gonna do that. But once you do, you get a different number. You get 7.9 times 10 to the negative third instead for your x value. So notice, I mean, there is a difference there. 8.2 times 10 to the negative third versus 7.9 times 10 to the negative third. It's not a big difference, but it is a difference. Once you find that number, then you can plug it in for x down here. Okay? That's our H plus concentration, our H3O plus concentration. So that's basically telling me out of the 0.1 molar solution we had originally, 7.9 times 10 to the negative third of that H plus actually ionized. Okay, so if I want to know a percent ionization, what you do is you take 7.9 times 10 to the negative third, whatever you basically do the same thing you do when you're doing the simplifying assumption, checking the simplifying assumption. You take the 7.9 times 10 to the negative third divided by your initial concentration, which was 0.1, and then, well, times it by 100. If I can do this in my head. Is it 0.79%? No, 7.9%, right? Yeah, 7.9%. Of course I can do that in my head. I just did it over here. Okay. So 7.9% is your answer on that one for your percent ionization. And then you do the same thing for the 0.010. I'm not going to work all the way through that one. But let me ask you this question. Could you use the simplifying assumption on that one? That one might end up being even worse than the first one, right? Because we're starting with an even lower initial concentration. So to say that whatever number we get for x doesn't matter when it's 0.010 instead of 0.10, it would actually matter even more. Okay, so you can't make the simplifying assumption for either one of those. But that's how you find your percent ionization. Now it's interesting that the percent ionized here, if you look in the book, for the second one, it ends up being 23% once you work it through and solve it the exact same way. 23% for letter B, which I think is kind of interesting because that's a much higher percentage than when you have the higher concentration, right? So that's kind of weird. So actually, if you look at the graph on page 687, it shows you that relationship. And it basically shows you that the higher the concentration of your weak acid, the less of it dissociates. Okay? And that's a Le Chatelier thing. All right? So if you think about this, and maybe here's where I should have written it correctly. I'll just write the equation up here the correct way. So if you've got your HF plus H2O in equilibrium with H3O plus F minus. Whoops, that's not a minus sign. That's a 1. So if you are diluting this solution, if you're making it less concentrated, which direction is that going to push the equilibrium? What are you doing to dilute it? You're adding water, right? So adding a reactant pushes it this direction, right? So that's why we end up with 23% ionization here, because we have more of the acid, right? If it's more concentrated, you're removing some of the water. Kind of think of it that way. So you're pushing it back towards the HF. So it's just a Le Chatelier thing, all right? It's just kind of an interesting thing to notice on that one. All right, and then polyprotic. We need to talk about polyprotic acids real fast. I don't know that they're going to give you one where you actually have to work through a problem with a polyprotic acid, but it's good to be aware of what a polyprotic acid is. Basically, it just has more than one H that can be given off, all right? So they give some examples here, and this is in the book as well, of some different polyprotic acids. Some common ones you might recognize: carbonic, citric, maybe phosphoric, sulfurous and sulfuric acid. So, I mean, there's a few fairly common polyprotic acids. One of them is a strong acid, which, if you look at it, sulfuric right here on the chart, H2SO4, first Ka, large. That's all they say. Because it's a strong acid, but it's only a strong acid with respect to its first hydrogen that comes off. Okay, the first hydrogen will dissociate completely, but then you end up with HSO4 minus. After that H2SO4, the first H comes off, then you end up with this, HSO4 minus, and then you can actually write that as an equilibrium, because then it has a Ka for its second hydrogen. All right? And you end up with H3O plus SO4 2 minus. And this one doesn't like to come apart as much in water as the first one does. All right, so that's why. And now it's still a fairly high Ka compared to the rest of these. You know, even compared to most weak acids, that HSO4 is a pretty strong acid. But that's kind of the idea there. So then they're saying if the difference between the Ka for the first dissociation and the subsequent Ka is 10 to the third or more, then you can basically just say the pH only depends on the first hydrogen that comes off. All right, so for example, ascorbic acid, I guess, is a good example of that. Its first Ka is 8.0 times 10 to the negative third. Second one is times 10 to the negative 12th. In other words, after it loses its first hydrogen, that second one does not like to come off. Right? So you can basically say that any of the H plus that is added to the water is coming from that first hydrogen, not from the second one. Okay? And that actually makes solving the problem quite a bit simpler when they ask you to solve the problem for a polyprotic acid. They're not going to give you a problem with sulfuric, I don't think, because then, you know, you sort of have to treat it like a strong acid and treat it as an equilibrium problem at the same time, and that's a little complicated. The one they give you in the book, I think, is for phosphoric. No, it's for carbonic. Did it used to be phosphoric? I feel like there used to be a phosphoric one in there, but maybe not. Okay, so for some, like citric acid would be a good example of where you'd have to take at least the first couple into account, right? Because with citric acid, for the first hydrogen to come off, it has a Ka of 7.4 times 10 to the negative fourth. The next one is not all that different
Call the main office.
to the
You're in
negative
building.
fifth.
Office.
So yeah, some of them you
Call
would
the
have
main
to take the second one into account, and that becomes a little bit of a pain. But for some of these, for the ones that you would probably see a problem on, and honestly, I'm not going to give you on your test, I'm not going to give you a polyprotic where you have to work it all the way through and do all 3 hydrogens, okay? But I'm just going to show you kind of how that works so you get an idea. Sorry, this isn't subscripted. I got frustrated, so I decided not to. The solubility of CO2 in pure water at 25 and 0.1 atmosphere pressure, and then it tells you the normal concentration of CO2. That at 25 degrees Celsius and not all that much pressure, this is how much CO2 you can get into water, which is not very much. CO2 doesn't like to be in water because it's nonpolar. It says the common practice is to assume that all of the dissolved CO2 is in the form of carbonic acid, which is H2CO3, produced by the reaction between the CO2 and the H2O. And I forgot to put the rest of the question. The question is, what is the pH? Here, let's do this. pH equals what? Okay, so we could solve for the pH of this
Mr.
thing.
Waters, contact the main office, please.
Because we have the 2 Kas for the carbonic acid. Now the nice thing about this one is that the first Ka and the second Ka do differ by a factor of 10 to the third or more, right? So you got 4.3 times 10 to the negative 7th. Actually, you don't see that unless you're looking at the book. But carbonic, 4.3 times 10 to the negative 7th versus 5.6 times 10 to the negative 11th, okay? So there's a difference of 4 in their exponents there, so that's greater than a 10 to the third difference. So that's kind of nice because we can basically just use the first one to figure out what our pH is. So then you're just solving it like most of the ones that you've done before. So you would say H2CO3, and again, I'm going to be lazy and write it this way, H plus HCO3 minus. Okay. I don't want to make any assumptions here. Everybody okay with that being the weak acid equation for this one? Basically, you're just losing a hydrogen. Okay. So then if you make an ice table for this, we know that we're starting with a 0.0037 molar concentration and none of the other 2 to start out with. And plus x, minus x, everything's still in a 1-to-1 ratio here. 0.0037 minus x, and x. So then you're just working it through the way that you would any of these other problems at this point. And I think that's really all we need to talk about, other than let's say that you did have to go ahead and figure out the second one. Let's just write the reaction for Ka2, because this would be Ka1, right? So Ka1 is equal to, I lost it. Here we go, 4.3 times 10 to the negative 7th. So if I want to write the Ka2 reaction for this one, then I would take the HCO3 that gets created in step 1, and then basically do the same thing again. So now that dissociates and makes another H plus, and then CO3 2 minus. And the Ka for this one would be 5.6 times 10 to the negative 11. Okay? So then, let's say those 2 Kas were not a difference of 10 to the third or greater, then what you'd have to do is whatever number you get here for your x value, for your HCO3 minus, that would be the initial number that you plug in up here in another ice table that you put together. Okay, so whatever your x value is, that would go in the initial column up here. And then The difference here would be this is not
Roderick
0.
Ward. You need to report to the main office, please. Roderick Ward.
And again, I don't think you're going to see a problem like this, but the H plus would not be a 0 at this point. Why not? Because we already have some H plus from down here, right? Okay, so whatever we find for X, that's going to go up here, but then this would also be X. Now we could say 0 of this to start with, right? And then you just work it out from there, okay? I just want you to understand conceptually how you would solve that. I don't want you to I don't care if you are able to work it all out and get it completely right, okay? But for this one, because there's such a big difference between the two KAs, you don't have to do that. You can completely ignore this part because guess what? The amount of H plus that you're going to get at the end here still basically just going to be X, right? Whatever this value was up here, it's not going to change very much by dissociating the second time, okay? So that's your polyprotics. I'm trying to think if there's anything else. The one thing that you really do need to know how to do with a polyprotic is if they ask you to write the reactions. And actually, let's practice one of those because I think that was one they used to have in the book that I kind of liked. Let's say you've got something like, let me just erase all of this. Let's say you've got something like H3PO4. So you've got H3PO4, okay? And they ask you to write out the Ka1, the Ka2, and the Ka3 reactions for phosphoric acid, okay? So the first one, basically, H3PO4, you would just say, okay, the first one is going to be, it gives off its first hydrogen, and then what's left? H2PO4 minus, right? Then, so that's your Ka1, right? And that's, you know, the majority of the hydrogen that comes off is going to be that first hydrogen. But then you've also got H2PO4 minus now, and that one could also give off a hydrogen, an additional H plus, and form HPO4 2 minus. That would be our Ka2. All right? And then you could also, finally, because there's still a hydrogen that could come off of this thing, so then you could have HPO4 2 minus, forming H plus and PO4 3 minus. And that would be your Ka3. Okay, and every time you go down in any polyprotic acid, Ka1 is always going to be greater than Ka2. Ka2 is always going to be greater than Ka3, and so on. Okay, I mean, you really won't get more than 3 most of the time. But does that make sense how you write those reactions? Okay. I think that's pretty much it for the polyprotic stuff. So, yeah, we'll talk about weak bases next time, and there's not a lot different with the weak bases than with the weak acids. And then we'll talk a little bit about the relationship between Ka and Kb. Because with weak bases, you get a Kb instead of Ka. All right, that's it. We'll see you in class tomorrow.